Welcome to the Jodrell Bank Radio Observatory, home to the Giant Lovell Telescope. In this programme, we're going to explore new perspectives, because we're going to be listening to the sounds of the cosmos.
That's right, it sounds bizarre, but we're going to be bringing you weird and wonderful noises from right across the universe, including something that's never been heard before.
Coming up, Lucy Green reveals how it's possible to see sounds on a distant star.
And there it is. That is what I've been after.
We'll find out how sound waves sculpted the beautiful and complex universe that we see around us. Yeah, that's the universe 300 years, 1,000 years after Big Bang. What do you reckon?
Oh, well, that sounded like a car going past, doesn't it?
It did a bit.
Yeah.
I'll be talking with Tim O'Brien about one of the most evocative sounds in the universe.
Oh, here we go. Let's
See something coming through. The sound of a star that has collapsed in on itself.
heartbeats. Yeah, exactly.
And we'll discover how to take amazing images of the night sky with just a mobile phone.
Oh, the moon. That is amazing too. Wow.
Everyone knows that in space, no one can hear you scream. And that is technically true. In the vacuum of space, sound waves can't travel.
But there is plenty of sound in space. Imagine the crackling of lightning amongst the clouds of Jupiter. Imagine the whisper of the wind on Mars. But all of those sounds are trapped. To access them, we have to use our imaginations, our theories, and our equations.
By listening to these sounds, we get a new perspective on what's out there and see things that were previously hidden, even in our own star.
There's a problem with the sun. When you look at it, you see what appears to be a broiling and beautiful surface, but all the real action is happening deep beneath that surface.
In fact, by using sound is the only way that we could delve beneath that surface and see what's going on internally. And that's just what Lucy Green has been doing.
Our seemingly silent sun is actually alive with sound. These are the genuine sounds of our star, sped up to bring them into the range of human hearing. They're generated from deep below its surface and are a vital tool that's helped us understand its inner workings. I love listening to these sounds of the sun. They're so alien, and they evoke a totally different character, a different side to the sun than the one I normally see when I'm studying it. The fact that we can listen to the sun at all, though, is incredible. Between us and the sun is 93 million miles of essentially empty space. It's a vacuum out there, and the sounds of the sun can't travel directly to us. Our ability to hear it, and everything that we've learned along with that, comes down to the very nature of what sound is. Sat here, I'm surrounded by sound. Voices, clinking of cups, the whoosh of the coffee machine. All these sounds are created by the same basic process. Vibrations. Vibrations that pass through the air to our ears. And the same is true within the sun. Turbulent regions of gas create sound on an epic scale. But it appears silent to us because there's no medium, no air or gas to transport the noise. However, we can detect these sounds because if you know the trick, it's possible to see sound. What we need is something called a Chladni plate and some salt. Give it a good covering. You immediately see that the salt is starting to move. And it's starting to take on a pattern. And there it is. That is what I've been after. The salt takes on a pattern when I make the sound. The vibrations of the plate are creating the sound that goes into my ears, and it's also moving the salt around. And you can see that with each note I play, the pattern changes. Oh, beautiful. And that is the key thing about these plates. It's the patterns that are created are unique for the particular sound. And that means that even if I can't hear the sound, I can't hear the effect of those vibrations, I know what notes are being created by looking at the pattern. And it's that principle that allows us to tap into the sounds of our star. What I have here is an image of the sun taken with the Solar Dynamics Observatory, and it's a colour-coded image. The black regions show us where gas is falling away from us, and the white regions where the gas is rising up. And it creates a very complex pattern, but essentially it's exactly the same as we made here with our Chladni plates. Now, it may seem hard to believe, but we can extract from this rather messy image the very particular patterns that are associated to particular notes inside the sun. And that is how we reconstruct the sounds that the sun has. But what's truly fascinating is that through studying these sounds, we can get a snapshot of the internal workings of our star. Thanks to work by people like Bill Chaplin. Okay, that must be one of the big pipes.
Yes, so straight away we can tell that just from the very, very low tones, the low pitch, the low frequency of that's one of the biggest pipes here. And the frequencies at which the pipes resonate, that tells us something about the size of the pipes, but also as well something about the gas inside the pipes here, just air.
But how does that relate to the sun and what we see as surface vibrations of the sun?
The sun makes the sound naturally, and it's trapped within the body of the sun, just in the same way that sound is trapped within the body of the pipes here. And so the trapped sound makes the sun resonate, but because the sun is a big ball of gas, the sound makes the sun gently breathe in and out. So we don't actually listen to the sun literally. What we do is we're seeing the effect, the visible manifestation, if you like, of the sound trapped inside.
Crucially, sound is affected by what it's travelling through. The changing temperature, density, even magnetic fields found in different parts of the sun all affect properties like the speed of sound trapped inside. And detecting these changes reveals the inner structure. It's a technique known as helioseismology.
We knew that a sun-like star should have a core where we're burning hydrogen into helium. That's what's powering the star and driving its evolution. And then the outer parts of the sun, there we have convection, so where we're moving energy from one place to the other, literally by moving hot gas. But it was with helioseismology that we got the first direct measurement of the depth of that outer convective layer. Also, we can measure the rate at which the material is spinning. And the profile that was found actually was not the one that theoreticians had predicted would be there. So that information that we've got on the rotation of the sun has been really important for people who are trying to understand how all of the magnetic activity, all the magnetic structures, how those are generated on the sun.
What I find amazing is that by looking at the patterns on the surface of the sun, we can not only listen to the sounds of the sun, we can also delve deep underneath its surface, and we can track and predict its future activity. It's an insight that would simply be beyond us if it wasn't for the music of our star.
There are sounds throughout the cosmos, but depending on where you are, not all sounds sound the same. We're used to sound travelling through the atmosphere of the Earth, but we can think about what sound would be like on other planets as well. We've got some software from the University of Southampton that will let us take our voices and send them to Venus, so I think we should give that a go. So I'm going to give you the microphone.
Right, I get the microphone.
I'm going to press record and you say something, okay?
So what would my voice sound like on other planets?
Well, good question. Well, the software will now process this.
So this is based on atmosphere, sort of density, various other parameters.
That's right.
So what would my voice sound like on other planets?
You sound like me. It's actually pretty close.
I feel like we're a space invader or something. Oh, take us to your leader.
That's right. And what's happening there is two things. So the atmosphere on Venus is this dense mix of carbon dioxide and a bit of sulfuric acid. So not a good place to be. But that density changes the way your vocal cords vibrate and also how the sound's transmitted because the speed of sound is different.
So it's just like in water, sound actually travels faster. So the more dense the atmosphere, the quicker the sound will travel, and therefore you get a change in the voice. But that was quite distinctive, wasn't it?
Yeah, absolutely. And it does illustrate this point that what you sound like depends on where in the solar system you are.
Now, we're here at Jodrell Bank, and the focus of much of the research done from this facility is on pulsars. Pulsars are extraordinary stars that emit beams of radiation that make them appear to flash. And the team here at Jodrell are hoping that they will help them to solve one of the great mysteries of astronomy. To study them, they use the massive Lovell telescope. Its dish is over 75 meters wide, and it observes the cosmos using radio waves. So Tim, we're here to look at pulsars, but pulsars are a special case of a neutron star. I find neutron stars a bit freaky, because it's something about 1.5 times the mass of the sun that could fit in Sheffield.
Exactly, yeah. I mean, it's a dead star. It's the core of an exploded star. So when the star explodes in the supernova, the core collapses to make this incredibly dense object. And these things, the exciting thing for us is that these things are spinning. But we can see them because they actually beam out light, and in our case we're interested in the radio waves they beam out from the magnetic poles. And just like the Earth, the Earth's magnetic north and magnetic south are offset.
Oh yes.
With respect to the sort of North Pole. The same is true for the neutron star. So as it spins, the magnetic poles sweep around like that, and that means that the beam that comes out from them sweeps around the sky. And every time it comes past us, we see a flash.
So just like a lighthouse.
Exactly like it's a cosmic lighthouse spinning in the sky. We see flash, flash, flash from the pulsar. And we're going to demonstrate that live with the Lovell telescope now. So I don't know, I think Ian, our telescope controller, will move the telescope on source.
Fantastic.
If you come and have a look at the screen over here, and basically we've turned those radio waves into a sound, and we can listen to that noise. And then what will happen is the telescope gradually swings onto the pulsar. Oh, here we go.
I can see something coming through. And that's it.
That's it.
That's the pulsar.
That's the pulsar.
Spinning round, sending that radio beam into space.
And you can hear the...
It's like a heartbeat.
Yeah, exactly. It's a dead star weighing more than the sun, spinning about 3 times a second, 26,000 light years away, which is really exciting because actually we've only just set this system up for you today to listen to this.
Well, it is fantastic. So pulsars seem to be fascinating, but why are they useful?
Yeah, I mean, they're actually this. I just turn that down so we can talk. The key role is in testing extreme physics, and actually one of the key projects that we're using, that the Pulsar group here and elsewhere in the world are working on with telescopes like this at the moment, is to use pulsars to try and detect gravitational waves.
I think you should say the elusive gravitational wave.
I definitely should. I mean, these things were, they're predicted by Einstein 100 years ago, but we've not yet directly detected them. They're really bizarre things. They're ripples in space-time. So if you can imagine somewhere on the other side of the universe there's 2 massive black holes at the centre of a galaxy, say, two galaxies have merged. These black holes are spiralling around one another. They produce this expanding pattern of ripples in space. And as those
gravitational waves.
Exactly, the gravitational waves travel through space at the speed of light. If there was sort of one coming through us now, which there almost certainly is, we're actually being stretched in one direction, and perpendicular to that we've been squashed.
So I suppose that's quite a distinct signature to pick up.
It is. It's always what you would look for. So the problem, you might imagine what you'd look for is simply whether something's longer or shorter as the gravitational wave goes past. But the trouble is the amount by which space is stretched is tiny. So in the case of the ones we're trying to pick up with the pulsars, it's a bit like the distance between the Earth and the Moon being changed by about the 100th the width of a human hair.
Ooh.
So you can imagine trying to make that
accuracy.
measurement.
Yes.
It's very hard to do. What's key about pulsars in this case is that they're very stable clocks, effectively. So we heard the thud of the pulsar 3 times a second. Because you've got so much mass spinning at that speed, it's a very stable system.
What sort of accuracy are we talking?
We're talking about measuring those periods to an accuracy of basically a nanosecond, so a billionth of a second. As space is squashed and stretched as a gravitational wave passes by, those pulses are bunched together or stretched apart.
So you'll see a slight change in the timing of those pulses.
Exactly.
So when do you think you'll see one?
Well, this is the key. I mean, sometime in the next few years, we might detect a gravitational wave. And in a sense, it's a race. We're learning things as we go along, as we gather more and more data. But yeah, I mean, great hope with this technique.
I think that's fantastic. Thank you so much. Next, Pete Lawrence has ventured outside to bring us his star guide. But first, he's going to show us how to take fabulous images of the night sky with something many of us have in our pockets.
All you need with one of these, a telescope, and something as simple as this, a smartphone with a camera in it. Now, you might not think that the camera on a smartphone is sensitive enough to be able to take astronomical photographs, but it is, especially if the target is big and bright. Now, the one thing which really fits that bill perfectly is, of course, the moon. To see details on the moon's surface, you need shadows, so you'll get the best images when the moon isn't full. Start by holding the phone away from the eyepiece. Then I'm going to move it in closer and closer, following the bright dot down. Now, this is actually a bit trickier than it looks, because of the way the lenses in the phone and the eyepiece interact. But keep at it. There it goes. And I can just take a shot. And, oh, that's a nice one. Look at that. And I'm actually quite pleased with that. It's quite a nice image. There are lots of amazing things to see on the surface of the moon, and to find a selection of the best, check out the moon guides on our website, bbc.co.uk/skyatnight. For the last few days, some members of the Breckland Astronomical Society have been experimenting with smartphone photography. Brilliant, thank you very much. They've even managed to capture an image of Jupiter. Wow! That is...
It's not too bad, it shows them.
But you've got the main belts coming through there, and I bet that if the Great Red Spot were visible on that disc, you would actually pick that up.
I reckon I would have got it, yeah.
Which is amazing. But the other thing is that comes out, because Jupiter is a gas planet which rotates very rapidly, it's squashed, so it looks not like a circle, it looks like the circle has been squashed, and you can actually pick that out on that. You can pick it out very clearly, actually, that the planet looks less wide from top to bottom than it is from left to right. Incredible. Absolutely amazing result. And if you... Oh, the moon! One of my favourite objects. That is amazing too. Wow.
4-inch refractor.
Look at that. That is just incredible. You know, a few years ago, you'd have taken a picture with a digital camera and you'd have been very happy with that. Absolutely. And this is with a smartphone.
The hardest part I found, of course, is just trying to get it lined up and get it centered. Hold it steady enough to get a steady image.
That's it, isn't it? Yeah, yeah. Well, that is quite a fantastic image. You should be very proud of that.
Thank you.
Thank you very much.
Thanks.
And there's lots of interest in this month's night sky, but I think the highlights have to be the planets. So here's my star guide to what's coming up. As darkness falls on the 16th, Jupiter is due south, 2/3 of the way up the sky. If you have a telescope, look at Jupiter's disk between 10:30 p.m. and just past midnight to see a rare event. The shadows of Io and Ganymede, two of Jupiter's large Galilean moons, will be crossing the planet. In the hours following midnight, locate the Plough, which is overhead. Follow the natural curve of its handle away from the pan to locate the bright orange star Arcturus. Continue the curve to arrive at brilliant white Spica. The bright salmon-pink object above Spica is Mars. A little less than 2 outstretched hands to the left and slightly below Spica is the yellow-hued planet Saturn. On the 27th of March there is also a daytime treat. Using your eyes, try to find the moon at 9:20 in the morning, being careful not to look at the sun. 5 moon widths below the crescent, Venus will be shining away in the blue sky.
Well, now back to sound, because Tim has created an audio tour of the universe for us, including some things that no one's ever heard before. So Tim, where shall we start?
The plan is to start close and then work our way out. So we're actually going to start with Jupiter, and these are sounds from signals that the Voyager 1 spacecraft recorded as it passed by Jupiter. So let's have a listen.
I don't think I expected that.
No, it does sound a bit like a dawn chorus.
It does, and
but screechier.
It's a rather more erratic. It's more like rather lovely hummingbirds. Yeah, no, it's called the Jovian chorus, the Jupiter chorus. These chorus waves are actually produced by electrons that are spiraling around the magnetic field of Jupiter. So sort of from the north magnetic pole to the south magnetic pole, and as they spiral around, they produce these radio waves that we've turned into a sound here.
So we can hear this delightful noise. I think we probably had enough juice there.
Turned off on cue.
Good. Where shall we go next?
So we're going to actually stick with Voyager though, actually. So we're going to carry on with Voyager back until just a few years ago when Voyager left the heliosphere. It's basically the edge of the volume of space that's influenced by the sun. What you're hearing is the rate of cosmic ray particles hitting the detectors on Voyager.
Oh.
So high pitch, lots of particles.
Whoa!
Oh,
That's quite significant.
And that was it.
So that was
the
the
point at which it left the heliosphere.
And that marks the end of our solar system, effectively.
So those particles are sort of trapped by the magnetic field of the sun, and as it passed over that invisible boundary, actually, where those particles are gathered, then you hear the sort of flux, the numbers of those cosmic rays drop significantly, which you heard in the sound there.
But I find it fantastic because Voyager was launched in 1977, travelling at 10.5 miles a second out to the edge of the solar system, and now it is officially beyond.
Yeah, that's our first interstellar messenger, basically.
That's still sending back information. But Tim, I want to ask you about your own research, because something rather exciting happened just a few weeks ago.
So I spend a lot of my time working on things called novae. We now know the stars exploding and becoming very bright. And one of these popped up in the constellation of Scorpius just a few weeks ago, and we've been monitoring it with telescopes around the world. And actually what we'll play now is the sound of the data from an X-ray telescope on board the Swift spacecraft.
Okay. Come on, you're grinning, so tell us what you heard.
There's two distinct tones there, I think.
There are, yeah, and what you're hearing are basically the X-rays coming from this explosion, and there's actually two dominant parts to the X-ray emission. So what you heard was a high frequency tone. That comes from the shock wave that's ripping out from this explosion through the wind of the red giant star that's in this system. And that produces high energy X-rays, which come into that sound as a high-pitched tone.
So this is just ripping through the material that's surrounding the white dwarf?
Exactly, yeah. So it's surrounded, the explosion happens in the white dwarf, the shock wave expands out, very hot gas, very high energy X-rays that you hear as the high-pitched tone. But then as that expands out, you actually start to see through it, and what you see is the surface of the hot white dwarf. that's left behind at the centre where the explosion occurred. Now that also produces X-rays, but it's rather cooler, they're rather lower energy X-rays, and that comes in as the lower frequency tone. And that actually dominates, that becomes very bright for a while, but then as the hot gas on the white dwarf is all used up, then that fades away, and then coming back, underneath it all, you hear the high pitch of the shock wave still expanding out into interstellar space.
Excellent. Well, I'm glad we heard it, and we've now travelled to a distant star, but we need to go much further than that, to the edge of the observable universe, because sound waves that once echoed there formed everything that we see around us today. Sound waves are a key part of one of the most famous images in science, the Cosmic Microwave Background, or CMB. This is the oldest light left in the universe, and it forms a picture of what the cosmos was like only 300,000 years after the Big Bang. To discuss the role of sound waves that we can see in the CMB, I'm meeting Sarah Bridle, and I've brought with me an interesting recording. We're going to talk about the early universe, which was a very different place from the one we see around us today. So what was it like?
Well, so early in the universe was much denser. So basically today we've got a vacuum in space, but if we go back in time to the early universe, the universe was much smaller, everything was much closer together, and we had this soup of elementary particles. So we've got protons, electrons, and neutrons, and they're all much closer together.
That means you can get sound travelling through the universe.
Right, so today the universe is virtually a vacuum, but back then the sound waves could propagate through this dense medium.
Excellent, if you had any sound waves. So what we need is a source of sound.
Okay, yes. Then some patches were clumpier than others, so there was more stuff in one place and less stuff in somewhere else. So then gravity comes in, and then as things pull together, then they heat up. So the universe is getting clumpier and hotter in this patch of the universe, and then actually it gets so hot that it pushes itself apart again. And
it's just the particles are moving.
Particles are moving and it's getting hotter, and the pressure of that heat pushes it apart again. And then gravity pulls it back in again, pressure pushes it apart. So we've got this oscillation, this wobbling going on in the early universe, which is a sound wave.
And so I've actually got a recording of what the sound would have been like at that point. Right. So we've moved it up 50 octaves so we can hear it. It's a very low note, but we've moved it up. So I hope you find this impressive. Yeah, that's the universe 300,000 years after the Big Bang. What do you reckon?
Oh, well, that sounded like a car going past, doesn't it?
It did a bit. Yeah. It's a complicated noise, though. To see them, we have to tune ourselves into the microwave region of the spectrum.
So at that time, the light is travelling around in the early universe, and it's optical light, so we can see, could have seen it with our eyes.
So if you were standing there.
Right, if you could be there. We can't be there. We wouldn't be very nice, so we shouldn't go there. But it's light we can see with our eyes. But now, as the universe has expanded, those light waves have stretched out, and so they become microwaves. And so we can look with special radio telescopes at these microwaves, and we can see a picture of the light which is coming towards us, has been travelling to us all that time since the universe was just 300,000 years old.
We've got that picture here. So this is a picture of the whole sky taken by Planck, which is a European satellite that's just made the best ever map of this light. And what can we see here, and how does it relate to what we were just talking about?
Well, we can see these sound waves. We're taking a snapshot, basically, of what these sound waves were like in the early universe. And we can see these red patches and blue patches. So where the red patches are, that's where the universe was hotter and denser, where it was really clumped together. And that patch would have then expanded afterwards. But the blue patches here are where it was cooler and more spread out. So in fact, those hot patches where there's lots of stuff, that would have then gone on to form the first stars and galaxies, and that we can see today.
So this is a recent image. Planck delivered its results, a year or so ago now. Is there more to learn from looking at the microwave background in the early universe?
Well, Planck also has polarised sunglasses, effectively, on it, so we're going to learn about the direction of the light, which is going to tell us even more about how much stuff there is in the universe.
Fab. Well, I hope you'll come back and tell us about that, and we never know, we might have found a more aesthetically pleasing recording of the early universe by then. Sarah, thanks a lot.
Thanks a lot.
That's it for now, but do remember to send your smartphone pictures in and we'll put them up on our website.
When we come back next month, we'll be talking about Mars and what 10 years of robots roving around the planet have told us.
And Mars is really prominent in the sky at the moment, so remember, get outside and get looking up.
Good night.